In today's video, we're going to take a look at how to do change of variables and also something called the Jacobian in 2 dimensions and also briefly in 3 dimensions. Perhaps it's useful to recall the situation in one variable. Oftentimes, in one variable, you're asked to integrate a function f of x from, say, an interval from a to b. And it's sometimes easier to do a substitution where, in place of x, you choose u of x to be a function, and you hopefully want the derivative du dx to also satisfy additional properties. But let's switch the perspective a little and see what's happening. When we're setting u to be a function of x, we can think of the function u as a mapping from the interval a to b along the x-axis into a new interval in, say, the u-axis. So we now have a completely different space, a different real line that we're going to denote by u. And u is now a sort of mapping or transformation from a to b into the interval u of a to u of b. So for simplicity, let's suppose u in this case you've chosen to be a strictly increasing function. All right, and it has non-vanishing derivatives everywhere. So we've mapped an interval to another interval. And conversely, there is also an inverse to u, which we could also denote g inverse of u or x as a function of u, which brings the new interval u of a to u of b back to the interval a to b. And so when we're doing a u substitution, this is all going on in the background, and we've transformed our integral f of x from a to b into a new integral, where the domain of integration, instead of from a to b, is now replaced by ua to ub. And the integrand also changes slightly. F is now written in terms of u, or in other words, we found what the inverse x of u is and we plugged it into f. And we also have to multiply by a scaling factor, dx du, which in our situation also coincides with 1 over g prime of x, which is perhaps a usual situation that comes up in one variable integration. All right, so this was one of the common tricks that we've seen in one variable calculus. And, there's also a physical intuition to what's going on in u substitution. For example, you might be given some sort of experimental data where x is time measured in minutes, u is in fact time measured in hours, and let's say f of x is the velocity of a particle at time x, and this velocity is in meters per minute. So what does u substitution tell you? Well, u of x in this case would be 1 over 60 times x, right? Just the conversion between minutes and hours. And the inverse in this case would just be x is equals 60 times u. And we could calculate out what dx du ought to be. And what this is telling you is basically it doesn't matter, it doesn't really matter, as we know, how you measure the time as long as everything scales correctly. So for example, if your velocity is just, let's say, 1 meter per minute, and you're integrating 1 meter per minute from a equals 0 minutes to b equals 1 minute, then you've traveled 1 meter. That's your integral. And what you're doing in u substitution, you're no longer integrating from 0 to 1 anymore, right? Because you're now integrating in hours, so you have to do the substitution from 0 minutes, which becomes 0 hours, to, 1 minute. Now it becomes 1 over 60th hours. However, f stays the same in this example if f is constant 1. But you're not just integrating with respect to du directly, right? There's a conversion factor that goes in. And you need to multiply by 60. And the resulting integral to no one's surprise, is the exact same as if you had measured everything in minutes. So one sees by this example that dx by du is a pretty crucial alteration term. It turns out that in higher dimensions, the role played by dx by du in one dimension does generalize, and that quantity, this generalized quantity, is something we call the Jacobian. But we're getting a bit ahead of ourselves here. Perhaps a better question at this point to ask is, what's the motivation for generalizing U substitution into two or more dimensions? Well, perhaps the easiest way to motivate this is, well, in certain cases you could simplify integration, right? In one variable, U substitution, was taught, or you learned it because you realized that in certain situations it really was a useful tool for you to be able to evaluate concrete integrals. This still holds true in very special situations in higher dimensions, but surprisingly perhaps it's actually less useful for this. So it's not a very good motivation, I'd say, to learn, why to do change of variables in higher dimensions. And the reason why it's less useful is it's a lot harder to change variables in a way that is helpful in higher dimensions, partly because there's only, in one dimension, there's really only one way for your domain to change, right? It always maps a portion of the real line to another portion of the real line. That's what U of x does. So it's mapping an interval to another interval. There's nothing weird going on. But as soon as you get into two dimensions, you realize that, well, now you're mapping a two-dimensional region to another two-dimensional region. So in fact, even if you find a substitution that changes your integrand to a nicer form, it might do something really strange to your integrating region. And as we know from setting up double integrals, how to set up the integrating region is oftentimes just as difficult as evaluating the integral itself. So it's very hard to optimally find a substitution that works well for both the integrand and the domain. But nonetheless, it's sometimes useful. However, you would hope for better motivation than just sometimes this thing is useful. So perhaps the real reason is oftentimes it's just physical necessity to have to be able to switch coordinates easily and be able to import all of the tools of calculus, like integration, when you need it in situations when you do change coordinates. So why are coordinate systems or different coordinate systems useful physically? Well, perhaps if you're considering just classical mechanics, right? Oftentimes, if you're analyzing a system with n particles that are colliding, a very useful change of coordinates might be the center of mass coordinates. All right, so you take the center of mass of your n particles and center your origin at the center of mass. And oftentimes, a lot of these kinematic problems are simplified in such a case. So you do a change of coordinates there. But let's say you have some sort of potential f of x that lives on your space. And now you've undergone this change of coordinates. Well, then if you need to integrate f of x, you'll need to be able to integrate f undergoing this change of coordinates so that you can work in this very nice new coordinate system that basically the physical system forces you into. So that's one reason why oftentimes you're forced into knowing how to change variables for integration. And this comes up a lot in physical and engineering problems. Perhaps that's a motivating factor for learning spherical coordinates, right? Why do you care about spherical coordinates in 3 dimensions when you have Cartesian? Well, one reason perhaps is if you just have, say, a point mass, well, then the gravitational field is rotationally symmetric, so it's very nicely described in spherical coordinates. Or, the same thing in electrostatics. The electric field is also spherically symmetric for a point charge. And especially in electrostatics, perhaps you'll end up, might care about solving certain partial differential equations, which are very nicely solved in spherical coordinates. but perhaps there are other aspects of your problem that you'll end up needing to integrate for, and in that case you really care about how to switch the coordinate systems properly. Now that we have some motivation for change of variables, let's examine the case in 2 dimensions. So suppose we have a map that's given to you by u of t is equal to t of xy. So in this notation, this is just meaning that we have a transformation t, which gives you 2 functions. A function u that's dependent on x and y, and a function v that's dependent on x and y. For change of variables to work in integration, we're always going to assume that these functions u and v are both continuously differentiable. So this is a technical condition that we won't worry about too much for the rest of this course. We can now draw our regions R in x and y, and also the region that it maps to in the UV plane, which is designated T of R. So the region that it maps to is going to be called the image of our transformation. And we're also going to assume that T is a one-to-one mapping that maps R onto its image. So one-to-one here just means that for every pair of points in R, if they're distinct points, they're going to get mapped to distinct points in U and V. So there's some sort of preservation of uniqueness of points. So just like being continuously differentiable, we're always going to assume that our transformations satisfy this condition. So given such a transformation, we could also have its inverse, which will designate T inverse, and this is going to be written or given by a pair of functions where x is now dependent on u and v, and y is a function that's dependent on u and v. So with this notation then, we're able to write down the formula for change of variable. And the formula is basically the double integral of any function over a region R undergoes a transformation. We could rewrite this as a double integral over our image T of R in the UV plane, along with suitably changing f to be in terms of u and v using our inverse, and an extra factor that is just like the adjustment factor dx over du we had in one variable. And this factor is the absolute value of a quantity that we have here, which is called the Jacobian of the map T inverse. And the absolute value of this quantity is exactly the analog we need for U substitution to work in higher dimensions. Let's now take a closer look at the Jacobian and see why it appears. So this explanation is probably going to make a lot more sense if you've seen matrices or linear algebra before. But even if you haven't, we can try and make sense of this. So if you just fix a point, uv, and the inverse of t maps uv to also a point xy, and we can imagine a pair of vectors at each of these points. So first, consider the vector with components 1, 0. So this is the vector pointing, the unit vector pointing in the u direction with tail at the point uv. Alright, so this lives at the tangent space of the point at uv. Now it turns out that a good approximation of what the inverse of t does to this vector is it transforms this vector pointing in the direction 1, 0 in the UV plane to the vector with components partial u of x and partial y, or partial u of y. And also we can consider the vector pointing in the positive v direction, 0, 1, and that gets mapped to the vector partial v of x and partial v of y. And if we look at the square that is defined by the left-hand side vectors, this gives a square of area 1. And on the right-hand side, well, these two vectors also define a parallelogram, and it turns out the area of this parallelogram is given to you exactly by the absolute value of the Jacobian. So we see that basically if you divide up in the UV plane the entire plane into squares of unit size length, then the inverse map T takes this grid and distorts it. And this distortion basically distorts the area such that each unit square gets distorted into a parallelogram with area given by this quantity, the absolute value of the Jacobian. This is important when we integrate because if you remember, the double integral over any region is just dividing up the region to tiny little either squares or rectangles or other shapes. And in this sense, this is telling you you're replacing your squares with these parallelograms, and each of these constituent parallelograms have such a distorted area. So far, this all seems pretty new. So let's ground ourselves and take a look at what this means in polar coordinates. So remember that in polar coordinates, we have essentially the inverse map giving you x and y in terms of r and theta by x equals r cos theta and y equals r sine theta. So that's t inverse, where t really is your transformation into polar, right? That's r squared is equal to x squared plus y squared, and the tangent of theta being equal to y over x. So let's compute what the Jacobian is for this change of variable. So here's the formula, and we plug in the relevant derivatives. So once we calculate the derivatives and then we just do some algebra, we find that the Jacobian is equal to r. Now, what we really want in polar coordinates is in the change of variable formula, we need the absolute value of the Jacobian. And in this case, because we're assuming in polar coordinates, r is already always taken to be greater than 0, this Jacobian is just going to be equal to positive r. So we just recover the same old formula we had before for integration in polar coordinates. And this matches up exactly with the general change of variable formula. An important thing to remember when we're doing these calculations is that the Jacobian itself is not always going to be positive. Alright, so it's very important to remember to put the absolute value signs around the Jacobian once you've calculated this. In fact, in the example above, had we just switched the columns and done the partial of theta first in the first column and then partial with respect to r in the second column, we'll see that the determinant, or the Jacobian, is going to be minus r. And so to get the correct formula, you'll need to remember to put the absolute value on that and make it positive. We'll see later what it means for the determinant to be negative, all right, so for the Jacobian to be negative, and it has to do with orientation, which is something that's going to come up much later in this course. now that we have a firmer grasp of what exactly the Jacobian is and what its absolute value means, let's return to the overall problem of changing variables and see what the actual steps are. So suppose you're given a double integral, and for whatever reason you need to change variables. Now step 0 is perhaps you need to decide on what a suitable transformation might be. So like we said before, in general in the real world it's pretty hard to find a transformation that works nicely for both your domain and the function that you're given to integrate. But in a class setting, sometimes you're asked these questions, so you should look for clues, and we'll see in a bit with a couple examples what some typical choices might be. So you should either decide on a transformation yourself, or perhaps in some situation you're given one already. The next step, which is step 1, is to find what the image is in the UV plane. So you're given a transformation that re-expresses your domain in the UV plane in terms of x and y, so you should draw out what this is. And getting this sketch is absolutely crucial, all right? And we'll take an example later to see what to do for this. Now the second step is to find the inverse of your transformation. So re-express x and y in terms of your new variables u and v. So usually this is easier said than done for the most general transformations, but once again, in this class and perhaps in exam settings, you'll see similar examples come up, which tend to be easier to deal with. Now the third step, once you have all the previous steps, is to calculate the Jacobian and take its absolute value. Then finally, once you have that, the fourth step is to set up, using the change of variable formula, your new integral in terms of u and v. And finally, as kind of an afterthought at this point, in step 5, you should evaluate this. Now in general, all of these steps are going to be very difficult in the real world, and oftentimes it's probably impractical to apply. But because this class is not the real world, you should be well practiced in applying these steps wherever it's possible in a given problem. As an example, a very common situation you'll see maybe in your assignments or on tests is changes of variable relating to ellipses. So let's find the area inside the ellipse given to you by x over a all squared plus y over b all squared equals 1. Now in this example, let's just, for convenience sake, suppose a and b are both greater than 0, even though it doesn't really matter because those quantities are squared anyways. We first want to formulate the area integral. And in this case, our region R is going to be the region inside the ellipse. And remember that the area of a two-dimensional region is just given to you by the integral of 1 over that region. Following our outline from before, let's start with step 0 and guess at a reasonable substitution to make. Now, because we're dealing with an ellipse here, its equation is suspiciously close to that of a circle. So let's just try substituting u is equal to x over a and v is equal to y over b. So those are the terms appearing inside the squares. And if we try that, the first step is now to figure out what the image of R is under this transformation T. So we'll first draw our starting region R in the xy plane. And really the strategy here is to always figure out where the boundary of your region maps to. And in our case, our boundary L is given to you by just a single equation, the equation of the given ellipse. And the image of this in the UV plane we could simply calculate just by plugging in our chosen transformation. And this just gives us u squared plus v squared equals 1. And that's simple enough to draw because that's just a circle of radius 1. So that is the image of our boundary L. And within this image of our boundary is going to be the image of our region, R. So the shaded region is T of R. Now, we can move on to step 2, which is to find an inverse for our chosen transformation. So remember, we need to find the inverse in order to eventually take the Jacobian. So right now we have u and v in terms of x and y, and some simple algebra then shows you the given inverse, which gives you x, y in terms of u and v. Step 3 is to find the absolute value of the Jacobian. And first we calculate the determinant, which is, in our case, simple enough because partial x, or partial u of x just gives you a, and we see that partial v of x is 0 because v does not appear, so that gives you a 0 in the corner, and similarly for y. Calculating all together, we get the determinant, or the absolute value of the Jacobian is just ab, because we're assuming a and b are positive. Our fourth step is to set up our area integral, which in this step is simple enough. We're integrating 1, and so in our change of variables, we're just integrating the product ab, which comes from the Jacobian factor, over our new region, which is just a unit circle. And so we could finish the calculation, and that just gives us AB times the area of the unit circle, and that's AB pi. Having done this example for this given ellipse, a really nice exercise for you to do at home or for when you're preparing for the next exam is to see if you could find the relevant transformations for the most general form of an ellipse. Right, so in this particular case, our ellipse was pretty simple. It was centered at the origin, but in general, ellipses could also have centers that are translated away from the origin. So maybe x minus c squared appears for some constant c. So go ahead and look up the most general form of an ellipse and see if you could guess and work out the change of variables necessary to turn a general ellipse into a nice looking region. Our next example is a bit more complicated when it comes to sketching out the transformation, but it's not too bad once you've seen one example of it. So here we're going to be asked to evaluate sine of x minus 1 y over x plus y over a region that's bounded by a set of 3 straight lines. Now, one of these lines, x plus y equals 1, you recognize as being coincidentally appearing within the integrand. So that gives you a strong hint on what you might want to try for substitution. And the strategies that we're going to do here will apply similarly to other integrals that you might see come up later on. So in this case, we could definitely set one of our variables to be equal to x minus y, which appears in the integrand, and the other one will try to be x plus y, which both appears in the integrand and also as one of the bounding lines for our region. So we could hope that this actually will make both the integrand and the region itself simpler. Let's see what happens when we try and map this out in step 1. Once again, we'll start by sketching out our triangular region in the xy plane first. And notice that we want to first figure out, like before, where the boundary maps to, and because the boundary here consists of distinct straight lines with different equations. I'm going to distinguish them by labeling them L1, L2, and L3. Now, in order to figure out what the image of this is in the UV plane, let's systematically work through the equations for each of these segments on the boundary. First is L1, images in the UV plane. We simply plug in y equals 0 into our substitution of u and v. So u is now equal to x minus 0, and v is equal to x plus 0. So both u and v are equal to x along the line L1. And because they're both equal to x, we can set them equal to each other, and we see that the image is a portion of the line u is equal to v. Specifically, we see that the parameter x goes between 0 and 1, so the endpoints of the segments are at 0, 0 in the UV plane and 1, 1. Moving on to the hypotenuse, L2. This is defined by x plus y equals 1 and y is between 0 and 1. So now, on the UV side of things, we'll plug in u is equal to x minus y, so that remains, but v is now equal to x plus y, which is equal to 1 on this diagonal. And now, for the first equation, we can actually simplify further, just using the fact that v is equal to 1, and that's equal to x plus y. We have that u is in fact equal to 1 minus 2y, where y is between 0 and 1. And this turns out to be along the line segment along v equals 1, where u now is between minus 1 and 1. And now L3 is awfully similar to L1, so we repeat the similar calculation, but in this case we get that u is equal to minus v, so we have the image as a line segment lying on the line through the origin with negative 1 slope. So now we have this upside down looking triangle that defines the transformed region T of R. Our second step is to figure out what the inverse is. Now, if you've seen linear algebra before, some matrices, then this shouldn't be too difficult for you, but as a refresher, we have two linear equations here, u equals x minus y, v equals x plus y. So one thing we can do is just add these two together to cancel out one of the unknowns. So in this case, u plus v is equal to 2x. And similarly, we can subtract them to cancel out the x. So v minus u is equal to 2y. And just dividing out by 2, we get the inverse, which gives us xy in terms of u and v. For step 3, finding the absolute value of the Jacobian, this isn't too difficult. We once again just plug in the formula. We have functions here that just have constant factors in front of u and v, so the calculation is not too difficult, and we find that the quantity we want is absolute value of 1/2, which is 1/2. Finally, in step 4, we can set up our integral in UV coordinates. And perhaps the mildly tricky bit here is we need to parameterize or describe the region T of R in UV coordinates. Hopefully that's a good excuse for you to remember how to set up these two-dimensional regions. And once we have set this up, we can evaluate. Now, you can evaluate this either directly, or there's a little trick here where you see that the inner integral is 0. And the reason for that is because minus v to v is a symmetric region about 0 with respect to u, and the integrand sine of u over v is odd with respect to u. Therefore, you're integrating an odd function over a symmetric region containing 0, and so the integral is always going to be 0. So with those two examples, hopefully you get a taste of what changing variables is like in 2 dimensions, and also see how difficult really the whole process is, even with some very simple and contrived examples. However, a good exercise might be to break these down into tiny steps, and for each step see how well you could adapt your techniques to figuring out the step. For example, if you're given a transformation, a good thing to practice might be to see if you could sketch out what the images of these transformations are. So that's just the process of mapping out the edges and doing that carefully. So before we end this video, let's take a brief look at what the situation is in 3 dimensions. So as you might expect, this generalizes really to any number of dimensions, within reason. Of course, it gets more and more impractical because we see just how complicated this situation is even in 2 dimensions. But it's good to know sort of what the procedure is. So first, if you want to do a substitution in 3 dimensions, well, you have one more variable, so let's call it w. Our transformation then expresses u, v, and w in terms of x, y, and z. And these are 3 functions, or 3 component functions, which we'll assume to be continuously differentiable and also one-to-one on the region that they're defined. Our Jacobian is going to be something similar, but we have a 3 by 3 matrix now. The top row of the matrix is going to be the partials of x. The second row is going to be the partials of y. And the third row is going to be the partials of z. Now remember that to even get to this step, we needed to find the inverse of the substitution we made, and that's a very non-trivial thing to do in general. So remember that when you're asked to find the determinant of a 3 by 3 matrix, in this case particularly the Jacobian, the formula really consists of adding together the products along the main diagonals as follows. So having the equation now for the Jacobian, we can now write down what the full change of variable formula ought to be. And this is extremely similar to the 1 and 2 variables. Finally, as a good exercise, we can look at this situation in spherical coordinates. So if you remember back to spherical coordinates, hopefully you know what the volume element ought to be, so what the absolute value of the Jacobian should be. So let me remind you what the spherical change of variable is. And I'll leave it to you to do the Jacobian calculation above and see if you get what you expect.